Hello, Professor. Today we'll be presenting our project on single agent to swarm proximal policy optimization based reinforcement learning for autonomous tile cleaning. And this presentation will be given by Group 5, and our team includes Mohamed Elmohandes, Abdelrahman Ahmed, and myself, Mohamed Noshin. And for the table of contents, we'll start with the introduction where we explain the motivation of decentralized learning. Then we'll go into the methodology for both the single agent and multi-agent setups. Then this will be followed by the results, the key findings and discussion, and then we'll have a demo of the whole project and a conclusion to end with. We'll start with the introduction. So most robotic cleaning systems today rely on a single robot. And this works in a small space, but for a larger environment, it becomes slow, repetitive, and inefficient. So in order to tackle this problem, multi-agent system uh, has been proposed because it offers better coverage and is more efficient. However, they often rely on a centralized control or a communication or a shared policy approach, and this can add complexity and can reduce scalability. So, our goal here is to build a fully decentralized swarm where each robot can learn and act independently using reinforcement learning. Now, of course, the question is why decentralized learning for robotic swarms? So in the answer is again in centralized systems, if the communication or the shared controller fails, the system can collapse, and that's not practical in a real world setting. So we propose a system where each robot learns its own policy using only what it sees and experience without any communication or any shared model. And this makes the swarm more fault tolerant, scalable, and easier to deploy in dynamic environments. And just to give an idea of the difference, or just to give an idea of what's the coordination paradigms that we have introduced in the project. So we'll start with the single agent. In a single agent system, there's only one robot. It is simple, but it is not scalable. In a multi-agent setup, several robots work together, I mean, often by sharing information between them, as indicated by these lines. And in a swarm system, like the one that we have implemented, all robots operate independently. And in this case, there is no messaging or coordination, and each agent learns on its own, and the group behavior emerges naturally from how they interact with the environment. Next, we will discuss the reinforcement learning algorithm that we have used, and that is the proximal policy optimization, or PPO in short. So it is a type of reinforcement learning where the robot improves by trial and error. So here's what it happens. So basically, the robot or an agent observes the environment, like detecting a dirty tile or sensing a wall, and if and it then takes an action such as moving or turning, and then the environment responds with a reward. It can be a positive if it cleans something, negative if it hits a wall. And what happens is that PPO uses this feedback to update the robot's decision making policy so that over time it learns how to clean more efficiently. So each robot runs this process on its own without any communication or shared parameters. So this is what it makes it truly decentralized. And in order to build this and test the algorithm that we have implemented, we have used a simulation called VBots. So in this slide, it shows the four key steps that we have followed. So in step one, we have created the model in which, so here we have created the environment and the robot setup. So the robot we use is epoch, and we just placed it in a grid based arena. In step two, we wrote the PPO controller in the Python. So each robot runs its code independently during the training. Third, we simulated it for both the single and multi-agent systems and observed how the robots learned and moved over time. And fourth, we compared the results, and this can be again implemented and tested in real world setting. For the contribution, we have four contributions. The first one is that we are the first one to introduce a reinforcement learning framework for swarm cleaning. So in this setup, each agent learns independently with partial observability in the domain of cleaning systems. The second contribution is the decentralized PPO framework. So the decentralized PPO framework is actually implemented by a work by Fatma Kumar, So here he has implemented this framework, but only for a single agent. So we have taken this and implemented for a swarm setting where uh, without a coordination system for each agent. And of course, we have created the simulation environment by developing a VBot simulation to test the swarm behavior. And finally, we have scaled from single agent to multi-agent swarms, and this will be the main contribution of this work. Next, we will move on to single agent methodology.
So single agent methodology. We can see that the hardware we used is a 3060 GPU, an AMD Ryzen 5 5600H CPU, and a 16 GB of RAM. The environment is basically a 2x2 environment with 10x10 grids, which covers a total of 100 grids. You can see the red tiles are the obstacles, and the black tiles are the dirt tiles, and the white tiles are empty or basically clean tiles. And this is the Epoch robot. The Epoch robot is by default having proximity sensors and communication modules for like emitter and receiver devices. Algorithm used here is the Proximal Policy Optimization, or PPO in short. So what are the results and key findings and discussion? So as you can see here, this is a test that we have done. It is worth noting that these tests are done, or the policy is updated every episode. Later on, there will be a specific one I'll mention that does the policy updates every action. As you can see, there's a general trend of improvement. The reason we have negative rewards is because of we are penalizing the robot for having wandering around or basically going over tiles that are already cleaned. And we can see here that we achieve around 26 tiles cleaned, and the total was around 30. Was 32 tiles. So we have around 26 out of 32 tiles in just under 300 episodes. We did the same experiment, but rather than 300 episodes, we made it run to 600 episodes, and this is independent. So we started this from the beginning, and we can see that also there's a general trend, and also we reach around the best scenario, which is around 26. Now, we did another experiment with 2000 time steps rather than 1000, and we can see that it is actually not doing as well as the 1000 time steps. And we plan on doing more of these so that in the future work, so that it basically we do like a comparison between what is the most optimal time steps to use, and basically adjust the parameters, hyperparameters. And also we can note that there is a lot of fluctuations in all of these, and the reason is also because of the learning rate and some other parameters that we need to do some hyperparameter tuning on. Then we try to do it on updating every one action, and we can see that it doesn't perform well. This is because maybe it is learning in the beginning, and it doesn't generalize to the entire environment. So this also needs to be explored by doing hyperparameter tuning and changing the reward system, and maybe playing with the architecture. And we can see here that even though it does clean tiles like around 26 compared to the other ones, like 26, even a little bit better, 27. But the more we basically train it, the more it will be wandering around, and the less it will be actually cleaning the dirty tiles. And here we did a cumulative graph where basically you have an episode versus cumulative time steps. And what we are supposed to have is an exponential graph. We can see that there's some exponential or like some curvature here, but it's not really an exponential. So this, as I mentioned, needs to be done using hyperparameter tuning and other modifications.
All right, so I'll be talking to you about the multi-agent approach in general. This is basically just building up off of the single agent approach we had earlier. Of course, we're starting off by adding more robots, with each robot having a unique name, being cleaning robot X, X being a number, obviously. And we have shared the controllers between the robots. So like each robot gets its own controller. It is the exact same controller. And the supervisor is centralized just to make coding easier. But we want each robot to be an individual, which is why we're adding individual policies to each robot. And this is done through looping through all of the robots and assigning them a policy. We're also adding individual measures. This is like, clean tiles, the rewards, the steps. They're individual. They're not shared between different robots. At one point, we added sensors, for the collision avoidance. And I believe that is it. Now, because all of the robots are basically the same, they're homogeneous, which is important for swarm robotics, so we started training. Now, onto the results, key findings and discussion. We're starting off with 2 robots. As you can see, there is a general positive trend in both reward per episode and tiles cleaned per episode. Rows per episode, it would have continued rising a little bit longer, but we have a limit of 600 episodes, and we can see that it stabilized at about -100 reward. And as for tiles cleaned, you can see by the end here, it was basically each robot is cleaning 15 tiles each. Now onto the second, we have the sensors. Again, this is for collision avoidance. We also have another type of collision avoidance, which is that when 2 robots are in a single tile, they are punished. But this is different in that it senses any obstacle getting closer, and it punishes a robot for that. We also have 600 episodes here. It stabilizes slightly lower than -100. This is probably because there are more factors affecting the reward. If we were to train for longer, it would have reached -100 or even higher. Again, this is stabilizing at about 15 tiles cleaned by each robot. As for the 6 bots, we couldn't train for much longer than 100 because of hardware constraints. It would take too long. As you can see here, it's a bit noisier, again, because of how many robots there are. There's a general upward trend, which is good to see. But over here, even though we increased the size of the environment for the 6 robots, we may have not made it big enough, because although there is a slight general upward trend, it's not very noticeable. And this could be because they started cleaning very well right off the bat, because there wasn't a big enough environment to explore. As for the demos,
Okay, so this is the Weebot simulator. For the demo, for the first part, for the single agent, we can see that the environment is generated with dirty tiles, which are these, and the obstacle, which are the red ones. And you can see that the obstacles also have a height, and also has like physics and bounding object, so that basically when the robot comes or like hits it, it will not be able to go through it. As you can see, if I speed this up, the robot will be able to clean some tiles, and initially it's random because the policy, like, it's just started training, but over time it will be more much better in knowing where the tiles are and so on. In the code, we can see that this is running for actually 1000 time steps, and we are updating the policy every action taken. If we want to update it every episode, we'll just move this function call over here. If we go up, and we can notice that there are some variables that we can change, for example, the max episodes. So this one will run all the way to 600 episodes and generate for us the results. As you can see here, the first episode finished, and we have a reward and the clean tiles. And more information about the rewards and the architecture and so on is in the report. Moving on to the multi-agent.
okay, so I'll be showing you the demo for the swarm. It's only a 2-bot swarm, just so everything can run faster. As you can see, even though I'm having it on the faster option, it's not running that quickly. I'm not entirely sure why, to be honest, but it just is. Over here you can see the uniquely named bots 1 and 2. They just started training right now, so they have jerky movements. They look random. That's completely normal for the first episode. As for the code itself, it's not entirely different from what Mohamed showed you. The main difference is we have a parameter over here showing you the number of bots, and there are many parameters that we are looping over for multiple bots. Like policies over here, we have one for each bot. And I believe that is it. Yeah, thank you very much.
To conclude, our decentralized PPO approach enabled agents to coordinate without any communication, which led to an efficient tile coverage and fewer collisions. We have also found out that episodic training worked better than per step updates. So this helped in stabilizing the algorithm learning. And for future work, we plan to test this setup in a dynamic environment with real hardware and to explore how it scales in practice. Thank you.